And there's time for some random numbers. We have three types of algorithms. They are deterministic algorithms. It is a sequence of operations that gives the correct answer, and if we repeat it, it gives the same result. For example, if we inverse a matrix by the Gauss-Jordan elimination, full pivoting, it means that we always find the largest element and make one step of the Gauss elimination using this element. Then we'll get the inverse matrix, and it's defined by the algorithm. Then there is a Monte Carlo algorithm. It uses random numbers, or on a computer pseudo-random numbers. That is something that is essentially looks like a random numbers, although it's generated by a deterministic algorithm. Then we'll get a result that is correct within certain error margins or certain probability. Something like 5 plus minus 1. For example, if we solve the traveling salesman problem, we did it by simulating annealing, which is a sort of Monte Carlo algorithm. We'll get a result. We are not sure that this result is fully true, but if we do it several times, we can get supposedly quite good results, but we may get always a different result. And then there are Las Vegas algorithms. They also use random numbers, but they use random numbers for a control. That is, finally we'll get a deterministic result. For example, we can control matrix inversion not by full pivoting, by the largest element in the remaining part of the matrix, but because this full pivoting may be demanding, but we'll use certain random number based algorithm to find the pivot from a set of good candidates. So such an algorithm will be good enough, but the actual order of operations will be different every time, but the result should be the same, except rounding errors perhaps. So to perform Monte Carlo and also Las Vegas algorithm, we need good pseudo-random numbers. Here is one simple example. Very simple. Nowadays such random number generators aren't used. It's based on multiplying a number by a certain reasonably large number, and by calculating the modulo operator, it means a remainder by division. If we use this value, it is quite easy to do very efficiently in a computer. Here there is an example of 1000 of random numbers in time. You can see that they look pretty randomly. Nowadays, usually the most popular random number generators are shift register generators. They use special bitwise operations and combine them in such a way that the sequence is essentially so chaotic that we can regard it as random numbers. The first example of a Monte Carlo algorithm, the Monte Carlo integration, also called random shooting or naive Monte Carlo. We can calculate the value of number pi by the following algorithm. We'll take a square which goes from -1 to +1 in x and y, and we'll shoot randomly and uniformly points, that is x and y coordinates, and we'll count all points that are inside such a circle. And if we divide this by the total number of points, we'll get the probability that such a point goes to a circle, which is the same as the ratio of the area of this circle to the area of the square. Here is an algorithm written in a certain language similar to Pascal. Let us say we have total number of points, certain counter that we will use. Here we will accumulate the number of points that are inside the circle. X and Y will be coordinates, that is real numbers, and this will be a function that returns a random number in interval from -1 to +1. So let's start this. We generate X and Y, and the condition that the point is inside this circle is that the distance from the center squared is less than 1. So in this case we advance this counter nu. And what is the value of pi? We know, as I have said, that the probability is pi over 4, so we multiply it by 4. This is number of hits and total points, and that's it. We can also estimate the standard deviations or uncertainty of the result. Actually, to use such an algorithm isn't so bad idea for complex multidimensional integrals. Here is how to do it in general. That is, an integral of a complex function over certain area in a high dimensional space is the volume or area of this area or object divided by the total number of points. Here is the sum of the function value of all randomly shot points. And here I have a computer code that shoots randomly 1000 of points, then wait 1 second and calculate the value of pi. Well, essentially this code calculates a few microseconds and waits 1 second, so let's speed it up so that I will not draw any points anymore. So now it's much faster, and you can see that the value of pi converges pretty well to the number that you know, including this error estimate. So we have 1 billion now, and I guess it is enough. The idea of calculating the value of pi using random processes is quite old. We can determine the value of pi by tossing randomly needles or whatever pins on a plane where there are parallel lines. Where these lines are d apart, and let the needle is shorter than this d. So this is a condition that we have here, and then the probability that the needle crosses a line is given by 2L divided by pi d. It can be proven quite simply. Here I enlarge this piece a bit like this, and I have a needle here. This needle is put out of, I will assume that I have a center here that was put randomly, and also the angle. Because of the symmetry, I can take care only of this distance from 0 to d half this, and also the angle can go from 0 to pi half because of the symmetry. And the question is when such a needle crosses a line, because I assume that I am below this line in the middle of these lines, it's enough to check when this needle crosses this line. And the condition is that L half times the cosine of the angle, it's this line segment, is larger than the current value of z, that is which we have here. If we draw the cosine here, we have this area. This area has a certain value. We can calculate it, and the probability is just divided or normalized. So from the integration over d here, dz, we have integration from here, that is the half. We divide by this length, and we continue with the integration, and the second integral is over the angle. And what we have here is the argument is something that I wrote in this way. This expression means that it's 1 if it's true. So my condition is that z is less than this, which actually is written here. So I integrate this. This pi half, which is written here, is this length. This is the normalization, because I shoot random numbers randomly into this rectangle, in fact, if I use these variables. Okay, so I integrate the cosine, and this is the result. That is, let's take a needle, let's throw it many times on such a lined paper, and let's determine the probability that it crosses the lines, which is a number of positive tosses, that is with needle crossing a line, to the total number, and this is pi. And also we can determine, giving it here without a proof, we can determine the uncertainty, like 1 sigma, that is standard uncertainty. So we have it here. Okay, so in this way we can determine approximately the value of pi. Well, so the Buffon's needle was another example of simple integration. So let's try this for a liquid. We need to calculate in general something like this. Here is the Boltzmann probability, and here there is certain function, maybe pressure, for example. But if we do the integration in this way, it means that we shoot randomly molecules into the space. And in this case, we would have very many overlaps. For overlap, the energy is high, this Boltzmann factor is very small, and we have poor statistics. So instead of this naive or random shooting Monte Carlo algorithm, we need something else, something that is called importance sampling. It means that we will sample those configurations that are probable more often, and we'll do it in such a way that such an average will be calculated quite simply by the arithmetic average of the values divided by the number of hits. But it means that all configurations will be drawn from the Boltzmann distribution exactly. Well, and this is called the importance sampling, because we have individual configurations with the correct probability, and then it's easy to calculate the averages. So, how such an algorithm is devised? First, let's choose a particle. We'll see that the best way how to choose a particle is randomly. So we have a particle. Then we try to move it. And we must be careful now. We must move it symmetrically from the origin. That is, we have a molecule, let us say here, and somewhere here we will have a new position of it. And this displacement must be symmetric around the center, which we can write in such a way that this u is a random number uniformly distributed from -d to +d, where d is a certain variable, certain parameter. In 3 dimensions, this is inside a cube. That is, we have points, we have 3 random points distributed randomly in a cube, and at the center of this cube there is the original particle position, and a new position is anywhere within this cube which is symmetric around this particle. That is, in other words, the probability of the reversed move is the same. Thus we move a molecule, and then we calculate the new potential energy. Here TR means trial. So this is the new energy, this is the old energy, and this is the energy difference. And the algorithm is now exactly like is written here. If the energy decreases, this change is accepted. If the energy increases, it may be accepted or rejected. And it is accepted with probability given by the Boltzmann factor, with beta being the inverse temperature. That is, you know that beta is 1 over the Boltzmann constant times temperature. And with otherwise, that if it's probability 1 minus this, the move is rejected. And why this? That's because always the probability ratio of the new configuration to the old one, which is given by the probability of the trial move to the probability of the original move, is given by this Boltzmann factor. Here is a scheme how it works. So let's have here certain configuration. I will move this green molecule and it moves here. And let the energy of the trial configuration is a bit higher. That is, the energy increases. It means that this Boltzmann factor here is less than 1. So I will accept this move with a lower probability, exactly with this probability. But now I know that there must exist a reversed move which has the same probability to be generated, but may be accepted with other probability, and the backwards move in this case is always accepted, because in the reverse direction the energy decreases, and vice versa. It means that in all cases of such moves or pair of moves, forward and backwards, the ratio of new to old probability is given by the Boltzmann factor. And it is assumed that I will have a lot of moves, and that I can move by a certain number of moves moves from any configuration to any configuration, that probabilities of all configurations will be given by the Boltzmann factor of the energy of such a configuration, because it works for any pair. For any pair there is a so-called reversibility, or so it's not exactly the same, it doesn't matter, or detailed balance. A detail for this algorithm will be: first, let's choose a particle. On a lattice models it will be a lattice size and so on to move. I have said the best way is to do it randomly. Then we'll create a trial configuration from a configuration which is here denoted by step number k, so that we add certain random numbers to it, or we can also draw a fully new position, but in any case it must be reversible. Then I'll calculate the change in energy, and the configuration is accepted. It means that the configuration at step k plus 1 equals the trial one, the generated one, with probability that I wrote like this. This together means that if the energy decreases, I would get here unity. I always accept this move, and if the energy increases, I accept it with this probability, and otherwise it's rejected. In the form of a computer code, this means I generate a random number from 0 to 1, uniformly distributed. This is the code only for this step. And if this random number is less than the minimum of unity and this Boltzmann factor, then I'll accept the configuration. And if it's not true, the new configuration will be the same as the old one. So I just copy it or use it. You can easily mention here that here I use the minimum, because I have a probability here, and the probability cannot be greater than 1. So this is a number between 0 and 1, a probability. But you can easily check that instead of this condition I can use simply this condition. Just because if the delta u is less than unity, I'll get a number bigger than unity here, but this is between 0 and unity, so this condition is equivalent to this condition, and the rest is the same. Also, the version 3 is closer to the algorithm that I wrote here, like literally, but it's fully equivalent. First I check this condition, this inequality for the energy. If it's valid, I'll accept the new configuration, and otherwise I'll do the step which is identical to this one. Here I spare one evaluation of a random number and one exponentation, which usually doesn't matter. And this I repeat, let us say, billion times or something like that. So this is the algorithm detail. This method is called, if I haven't said this, the Metropolis method. There are some versions called Metropolis Hastings. You can hear this, but it's not important how it's called. Okay. The first step of this algorithm is how to choose a particle to move. The best way how to do it is to do it randomly, because otherwise we can get into troubles. Of course, if we have one type of particles, we can take them regularly. it will be okay. If these particles are identical, then the algorithm will be reversible. I cannot distinguish two atoms of the same type. But, for example, if I have three species ABC, and I would plan the moves sequentially, let us say ABC, ABC, and so on, it's incorrect, because the reverse move is in different order, CBA, CBA. It's not the same. Similarly, for example, in an NPT ensemble, if I change volume, I can have one move, let us say move molecule A, move molecule B, change volume. Again, this is not reversible. The best way how to do it is to do these moves randomly with certain probability. Certainly, changing volume is a bigger change, so I have to do it not so often and more often to move molecules, but the principle is given. Other way how to do it would be, for example, from this I can use A, B, and well, we got C, but now I must put B again, and now A, and repeat. So I will repeat this, and this is reversible. You can check it easily, but I am doing move B twice as often, which need not be the perfect way. It depends on conditions. So okay, so the best way is to use chaos, then that control. We have usually molecular systems in chemistry, and you can easily imagine that in dense systems, if you move randomly a molecule too far, it will likely overlap some other molecule and the energy will be high and the acceptance probability will be low. It will not be efficient. On the other hand, if I move a molecule just a little, I will almost always accept this move because the Boltzmann factor will be close to unity. But it will be inefficient because I move a particle just a little during a step, so my system will change slowly. In order to optimize such a Monte Carlo simulation, usually we use a quantity called the acceptance ratio. It is the ratio between the number of accepted configurations to the number of all generated configurations or trial configurations. I call this chi, and this chi depends on the displacement d. The optimal, and d is quite variable for small molecules, large molecules, for example, for rotations may be different and so on. So this acceptance ratio is a better quantity to be adjusted so that the simulation is efficient. There is a rule of thumb that tells that the optimum acceptance ratio is about 1/3 or 0.3. Of course, it depends on conditions a lot, but usually 1/2 is less efficient. Sometimes even very short ones for special reasons are efficient. Here are results of simulations of Lennard-Jones fluid with this reduced temperature and density. Here is the displacement, and here is the estimated uncertainty of pressure. That is calculated by a method that I will explain in the next talk. And we can see that if the displacement is very long, that is here, it's inefficient. The most efficient value of d is somewhere here. But this curve depends a lot on conditions. It's not universal. A more universal curve is here, where we use the acceptance ratio, and here is the uncertainty. You can see that this point is this point actually. So if D is very long, the acceptance ratio is very short and it's inefficient. And the best efficiency here appears for about 0.3. There are special cases, like for very diluted systems, typically for systems close to the critical point in a fluid. Even if the acceptance ratio is very small, few percent, it may be efficient to use very long trial moves, like moves over the whole simulation box, because such moves will change the configuration a lot. And that's all for today. Thank you for your attention.